Thank you, gracias. So, Pablo invited me some time ago to give a talk here, and what I did is I took a tutorial that I prepared for IITC this year on backend memories, but looking at the audience and the topics, some of the areas of this tutorial may not be so adequate, so I will skip many foils, but I'll try at least to hopefully have some foils that motivate some thought, and please feel free to ask at any point any questions, discuss, whatever. Okay. Okay, we're not ready yet.
So let me mention to the people going later to the hotel that the bus will be at 6:30 at the door. So I will mention it at 6:25 during the process session, and that's the same bus that will be available for coming tomorrow in the morning. Here. At 9 o'clock. It departs at 9 o'clock.
Today it departs from here.
Departs from here at 6:30. So I have here the timetable. So sorry, there is some kind of problem.
It looks like my file crashed the system. I'm kidding. Okay, so here we are finally. Anyways, I'm now with KU Leuven, and however, a lot of the work that I'm going to show here was performed while I was at IMEC, and will summarize results of this research. Yeah, thank you. So anyways, this is... Yeah. The number is when the university was founded, so they are proud it's an old university. The key is probably something historic. I have no idea. Yeah. Thank you. So this is the outline of this tutorial that I gave, an introduction. There was a section on STG RAM, and then the resistive RAM part and a summary. I think I'm going to mostly skip that and just give a brief touch of the introduction, but also I don't want to spend too much time on that. But mainly one of the things we're looking at is basically memories can have different applications. The most interesting for industry is those that can replace these really mass market commercial memories that produce a lot of money for the companies that produce them, like NAND flash, DRAM, SRAMs in any logic circuit, and all of them are facing scaling limitations. However, for any memory to be able to go ahead and replace them, the list of requirements on criteria are very, very demanding. So it's actually very difficult, while these memories keep advancing, to catch up and beat them, because you need to actually be better than them to be able to replace them. So for example, to replace flash, you need a very high density memory to make it basically low cost. You need very good retention, etc. For DRAM replacement, you need basically unlimited endurance or very high endurance, etc. For SRAM replacement, it needs to be very fast, endurance, etc. Reliability in all of them is key. So a lot of difficult requirements, yeah. So one of the questions is if any of these emerging memories that we're looking at can replace these memories, or, of course, there's also possibility of niche markets, and many of them may end up there, or open a new large market that's also be commercially very useful, but that doesn't exist today, which is kind of the view of most of the people in the industry, that that's what they hope will happen. So I listed some of them. Every day there are new ones, so this is just some of the ones that we've been looking at. Back-end memory is something basically that's done after you finish your transistors in the metallization at some between level 3 and 4 or something like that. So that's why it's called back-end. And the memory is stored as a change in the resistance state, and you can switch between the states by electrical pulses. This is basically the common feature of all of these. And some of them are already implemented in the market, like phase change RAM, which is shown here, where basically by passing the current, you heat up the sample quite high temperature, depending on whether it's quenched or cooled down slowly, etc. You stay in crystalline or amorphous state. They have different resistance. So that's basically your memory. And it's already in some products, mainly NOR flash, etc. But it has limitations in scaling because actually you need to melt, etc. And so it's seen now that this would be basically a niche type of application memory. STT-RAM is now gaining a lot of momentum. A couple of companies have announced they'll have products in the market quite soon, Samsung and Toshiba. And they're aiming at really DRAM replacement, so very aggressive. Again, I had a section on this, which I can skip for this talk, but anyone that's interested, basically, maybe I'll just show a couple of foils on this one. And then the resistive RAM, which is the topic of this workshop, with the oxide-based memories and the sort of metallization cells or conductive bridge RAM as some of the main examples. I think this one I may skip. So basically it shows that for the storage type of memories, NAND, etc., you need really very high density. They don't need to be so fast. DRAM, SRAM, they tend to be faster. They're closer to the processor. SRAM specifically needs to be very fast, and the density doesn't need to be so high. So there's basically kind of different areas that you can target. And also whether volatile or non-volatile, and how the different emerging memories will fit into that landscape. And we can see here STT-RAM and a resistive RAM with the potential of replacing DRAM, flash, etc. But again, with all those constraints that need to be met, requirements before you can do that. A few words about the need for selector, because there's one clear message from a lot of the sort of industry partners that we have in terms of resistive RAM and its application. One of the big limitations is not the reliability or the endurance or the retention, because improvements have been gigantic and we're getting to the point where we can meet many of these requirements. But to make a very high density sort of circuit, you need to have at each cross point a selector. And there's no good solution for a selector. So I think today the most critical thing to answer to make this into a manufacturable product and to go into a lot of things is to have a good selector. Some, as was mentioned in a previous talk, think about devices where integrate the selector in the element itself, or external elements, but right now there's no clear solution for this. So it's clear. And as was mentioned before, in a large array you have sneak currents, so you really need to block all the other elements, otherwise you don't have a good readout. The larger the array, the more difficult the problem is. Okay, so of course you can always use a transistor as a selector. That's the easy way, but you cannot get to very high density. For DRAM replacement, that's easy. So if you want to do DRAM, you don't need to worry about the selector. And some of these memories like CBRAM were targeting DRAM replacement, so they don't have this problem. They will just use a selector. STT-RAM is also targeting replacement of DRAM, as I mentioned. Also they use a transistor, so they're fine. For other memories, you need a two-terminal selector if you want to replace NAND flash, for example. And one of the other issues with flash is that the NAND flash is going into a 3D scheme. So basically, the stacks that you're making are not as shown here, basically patterning twice to make the cross point, but with one of the the arrays is flipped vertically, and the main reason to do this is to reduce the number of patterning steps. It's just a cost-saving issue. So again, a lot of physics go into understanding these devices, but at the end of the day, simple solutions like flipping something up, saving huge amount of money in lithography steps may make the difference. When Flash did this, it put ARAM in a very difficult situation. You have either an ARAM that can do this or you cannot compete. Okay, so I mentioned I would skip the STT-RAM, but again, this is something that is now, for some companies, they're aiming at going to production quite soon, so for DRAM replacement. So if anybody is interested, we can talk about it later, but seems to be a quite useful technology. And I'll just go directly to the resistive RAM systems. Polarity was mentioned earlier in several of the talks. Initial studies of resistive RAM were in unipolar systems. Bipolar systems in general are seen as a more gentler type of switching. The disruption of the filament here is a kind of Joule effect, some really catastrophic event, and it can be recovered, but not as many times. So typically the endurance of these systems is not as large. This has much better endurance. So in general, So the trend is that most of the studies now are focusing on bipolar switching devices. They can achieve a lot higher endurance, they're more reliable, etc. And as was mentioned before, set and reset are believed to be associated with ionic transport by basically switching the polarity of the field. This was, in general, what were the goals of the ERAM program. Initially, we're trying to see if we could get into replacing DRAM or flash, and as I mentioned, for flash, the issue of density is a key, so the selector was one of the key considerations. So this is kind of a repeat of what I said earlier. Okay, so now moving into the different types, there are many ways of classifying them. I'm taking always kind of the practical sort of approach, so what, for the application, for the what is important. And from the application, one of the key distinguishing sort of parameters among different types of ERAM is what is the dimensionality of the conduction? Is this a filamentary conduction path? Is this an area distributed path? So we start by oxide systems in which you create a filamentary conduction path, as was described earlier, right? And so this conductive path is basically a vacancy enriched or oxygen deficient path in the oxide, etc. Another type of filamentary conduction mechanism in which the medium is an oxide is produced when you put an electrode with cations that have quite high mobility, like silver or copper, and they can basically migrate into the dielectric and create a conductive filament. This is the metallization cell or conductive bridge RAM. Next is examples of what was shown earlier today. Systems in which the resistance change is controlled by the interface. And last, systems where you have a true bulk transition, like in a mud insulator, mud transition material, etc. And in all of them, we were studying systems. Vanadium oxide was a case we're studying here. So I'll talk a little bit about this, maybe a little bit about this at the end. Filamentary conduction mechanism in oxides. So first of all, do we know that's filamentary? There was some sort of physical characterization shown earlier. There are other ways to, and one example, one actually interesting example was from a publication from Korea Seoul National University, where they, in collaboration with Samsung, they did some conductive AFM inside a high-resolution TM microscope, so you could actually visualize the filament, see that it was more conductive, and through the imaging determined that it was actually a different phase than the rest of this is in titanium oxide. So that was kind of a clear proof of the filamentary path. They have some idea of what's the dimensions of the filament, etc. Another general sort of trend that has been observed even before this happened, why people were claiming filamentary conduction, was the area dependence of switching, pretty much not area dependent. So suggesting that the switching was controlled by some spot in the, and not by the whole device that you're looking at. Another interesting thing here is that there's also in the cases that we're studying, not a lot of film thickness dependent. So that also suggests that the localization of the switching is not just in this dimension that you have a filament, but within the filament, that's some local part of the filament that's producing the switching, not the whole filament. And last, work done at IMEC by Robin de Graaf and other co-workers, inspired by some early work at Universidad de Barcelona, is that correct? So I think we'll hear more of that on Friday, is that correct? But he took a sort of model that was initially developed for reliability, trying to look at what happens when you break down an oxide, etc., which is what you do when you start these things, and started to apply it and basically to fit IV characteristics in this type of resistive switching systems. And I'll show more on this, but basically you can find excellent fits between this quantum mechanical conduction model and our experimental curves for very narrow filaments. So, yeah, that's another proof of the local characteristics of this switching. So I have a few more foils. So the basically model is looking as basically if you're an electron time trying to go through, this is just basically a conduction model, and you have a sort of narrow incision where you can go through in your oxide, and it's modeled as a parabolic potential well, and basically you have and on the other dimension is a barrier. So I hope I'm not taking too much of the Friday talk, because this was again developed in Barcelona, not here, but anyways, it was applied here. So anyways, this is basically a very simple quadratic sort of model showing the potential for, this would be the constriction. So yeah, the highest part there is basically the constriction. And this is the mathematical form, right? And so there are two parameters used. Wx is associated with the sort of dimension going across the layer, so it's the length of the filament, and Wy is the width of this constriction. And this is kind of a level moving up or down that determines basically how conductive is the filament. And it was shown that so one interesting thing is that in very narrow filaments we could find actually quantized conduction, so kind of substantiating that the application of this model was correct. And in this case, you could see up to 4 levels of conduction. Again, and one of the messages from this is that most of the people that were doing modeling were using types of models or representations that were ignoring the quantization of the conduction, how narrow were the channels, etc. And it's true, if you make a very thick filament, you can model it as anything else. This will not be relevant. But the important thing for the applications, if you want to make resistive ramps that can be used in industry, the conducting filaments need to be very thin, very small, because the resistance states, it cannot be too conductive. It needs to be quite resistive in both the high resistance and low resistance state. So this model actually is quite applicable to the type of filaments you want in circuits that are actually in applications. Okay. So as I mentioned, there are other models a typical model of the conduction is basically trap-assisted tunneling through a percolation path, but this is, again ignores the quantum mechanics in the constriction itself. In some filaments, where you can make thick enough filaments, you can just model it as a continuum change, and basically you have an area of high oxygen vacancy concentration, you get a conductive band here, etc. But again, in the filaments that we're interested for the applications, which are even in the low resistive state quite resistive, the IB is mainly controlled by this quantum mechanical conduction through the constriction. A little bit about filament formation and switching. Filament formation, breakdown of the oxide, creation of this high conductivity, high vacancy concentration path is film dependent, is film thickness dependent. It's a breakdown, classical type of breakdown mechanism. However, once we form the filament and you're switching, the film thickness, we found very little influence of the film thickness. So showing that the switching is quite local in the vertical direction, in the direction across the film as well. And again, indicating localized switching and being consistent with a constriction that's controlling the switching once you form the filament from there on. If you go to very thin films, again going from the left side here, that's film thickness dependent, you can have basically forming less cells, as was mentioned earlier, that's useful for practical applications. This is just examples of switching. We studied many material systems, but the half-film oxide cell was the most typical one that we studied intensively in all sort of forms and shapes and etc. So this is the typical stack that we're studying, not unlike what was done at E3, but they were using titanium instead of half-film. I think they're identical systems for all purposes. And general trends is the set tends to be quite abrupt. That suggests some sort of runaway effect, and the reset tends to be gradual, sort of self-limiting. And this is a general trend. The switching itself is associated, as I mentioned, with some motion of, for example, vacancies, etc., under the electric field. I'll go more into detail later. But one of the interpretations of this was that during the set, basically it's not self-limiting, it's enhancing, what is the word? Runaway effect. So you increase the current, that increases the temperature, that increases, and basically the mobility of the ions, so they move more, they make a more conductive filament. It's kind of some sort of runaway effect where temperature is quite important. Our group, I don't have it here, and other groups, the group of Rainer Wasser also showed that you can reach very high temperatures, and that explains basically how you can switch very fast. In the reset, however, you have the opposite. It's a self-limiting effect. You're increasing the resistance, so current goes down, temperature goes down, mobility goes down, etc. This is the conventional view. Robin begs to differ on that, and he presented in June of this year at VLSI this hourglass model, and the claim is that even at deep reset, you have not frozen in the state. So this idea is you're kind of freezing a state, frozen in a state, goes low temperature, nothing else can happen. He claims that even in deep reset, you have a dynamic balance between things. Nothing is frozen, it's just that you're in balance. And the balance is dynamic, and you can still see quite a bit of oscillations if you look carefully, etc. So in our systems, it's important, one of the things, we have a vacuum cap. Why? That you don't need it, you can switch without the cap, but the vacuum cap, that definitely creates a region next to it with a large number of vacancies. That helps basically the process of forming filaments without creating too much damage, so you can switch them better later, etc., etc. And you can see by XPS that indeed you have oxygen vacancies close to the hafnium, etc. So it's a layer, non-stoichiometric layer in between. This is kind of something similar to what's shown before, and I think this is the Reiner's published version several years ago of the fact that in bipolar switching, we believe just by changing electric field, you're moving, in this case, vacancies of oxygen ions in opposite directions, filling and emptying this part of the filament. I think I mentioned this before, the fact that in some cases, the filament itself, after formation, is a different phase. However, switching occurs within that phase. It's not that each time you switch, you're changing the phase. So, going back to the quantum mechanical model, one of the interesting things of doing a lot of fitting with this, that's what Robin was doing a lot of measurements and a lot of fits, basically, was that he was, one of the easiest things to look at first was the reset. The set is this runaway effect, a little more difficult, but the reset was kind of gentle, so you could look at it. And you could stop at any point and measure the IB, keep going, measure the IB, keep going, measure the IB, and trying to do IB fits at the different levels of reset as you're going to a higher resistance state. And what was interesting is that the main change while you're going into this deep reset, looking at this fitting, was on the width of the channel, not on the length. So that, in fact, the length of the channel is changing very little, and while you're changing the resistance stage of the filament, you're widening or narrowing this constriction. This is counterintuitive and definitely in contradiction with most of the models that were at that point around, where basically people were looking, is the length between the constriction and the electrode or something, between the filament or something. So it's controlled by tunneling through a varying length. And what this shows is not controlled by tunneling through a varying length of resistive material. You're just changing the width of the constriction. This was verified to death in many samples of different kinds. As an example, this is a different system. This was on the typical hafnium oxide. I'm not even remember. I measured, okay, no, this is not our typical sample. This was hafnium silicate fuses, different one, but the same thing happened with the hafnium oxide, with any resistive system that we measured, again, in this not very conductive filament, these very not very conductive filaments. And in this case, it's a quite different system, nickel oxide cells, same thing, exactly the same thing. So it seems to be quite universal property. I think there's a few faults here, sort of departing from this topic of the constriction, narrowing, or widening. Has to do with electrochemistry. We can go into that or not, but another of the questions was, where is this constriction? And in our view, and I think that agrees with many other people, when you go into the high resistance state, that's by anodic oxidation. So we believe the anode is a critical material, and whether it can oxidize or not and produce these things, so catalytic effect. And this was part of this paper here, and basically, so this I already mentioned. Yeah, so basically changing the anode, we could see that in some cases it was working, some not. So we would correlate to this effect. We could also see some evidence of TM yields basically showing anodic oxidation, in this case at the nickel oxide interface. I would say that yields evidence, you have to treat it very skeptically, because you're thinning down a TM specimen, trying to do chemical analysis very locally with a beam that's modifying your sample. So we found these results. We think they're probably correct. I would not say this is the most drastic evidence of the anodic oxidation, but they're consistent with anodic oxidation. What are the implications of this filamentary conduction? One of them is scalability. This is good news for scalability. We want to make these devices very small. If you want to compete, for example, with NAND flash or any of these memories, we have to aim at maximum 10 nanometer feature size, and even below that. So from our characterization, we believe these filaments on the type of resistance that we need are just few nanometers, even less. So it should be quite possible to switch cells that are on the 5 nanometer size. We couldn't make those yet, but we could make cells that were 10 nanometers by 10 nanometers, and not just one, but whole wafers of these cells. And they switch very well and very similar to the larger cells. So we basically showed scalability to 10 by 10 is not a problem. This was shown IBM 2011. That was the good part. The bad part is very small filament means actually, and also this fact of the constriction is localized also in the vertical direction, is that the number of atoms involved or vacancies, or it's small, so you start to see the granularity of that in terms of variability, etc. Few atomic jumps will impact drastically the conduction of these filaments, so there's a stochastic component of this RAM switching and characteristics that you cannot avoid. It's intrinsic. So that's something that you have to see if the technology can live with or not. You cannot change too much. Another example is in retention, the same problem. Okay, you leave this thing at certain temperature. The specifications for retention are not room temperature, it's some higher temperature. So there is some thermal budget, so you will get a few jumps of things. How many of those are enough to change the characteristics of your filament? And in fact, you also start to see granularity of the fact that these are small volumes. So there's an issue also with the variability of the retention. Some cells will lose its state quite fast, and some will take longer. I think this is quite well known. In terms of speed, one of the requirements is high speed. It's a trade-off with voltage. I will not get into that, but the smallest can explain this. In Rainer Basser's group, they have looked at this quite carefully, so I'm not getting into that. In terms of the retention and endurance, I did mention that there are some fundamental problems. The mean of the distributions in terms of retention works quite well, and we could associate or correlate quite well retention with basically diffusion of species out of the filament. There's still an issue with the distribution, so some of the tail bits will have problems. Endurance, we have achieved up to 10 to the 10 cycles, and at the beginning we had a lot less, maybe 10 to the 4. Going from 10 to the 4 to 10 to the 10 was not achieved by changing the samples. It was achieved by changing the cycling, the way we cycle. There was some early work here that I remember Pablo sent me some years ago, where they have showed that by tuning the cycling you could improve the endurance. I think this was taking this idea to death and really fine-tuning. And this was published recently, where, again, the idea that, for example, if in your cycling you have to balance the cycling, if you're pushing vacancies too much in one direction, they will pile up and at some point basically either disrupt the filament permanently or make it too conductive permanently, etc. So basically this idea of balanced switching. This was another thing that was published earlier this year, in which we're showing drastic improvement in the cycling characteristics and in the process window, and that was by adding a thin aluminum oxide layer. And I think I will not get into all of these details, but we're studying the standard system and cases for putting the aluminum oxide on the hafnium side or in the tinitride side. And basically this was quite interesting also to show that in this system it's anodic oxidation what is disrupting the filament, because there were some groups that were claiming the opposite, and I think this was proving that. And if you put the aluminum oxide in the anode, so that's where you disrupt the filament, you get all the nice properties of the aluminum oxide. So you get a deep, higher resistance state for the high resistance state. You get a better barrier, etc. So basically the main improvement was on the high resistance state with the aluminum oxide where the disruption is happening. It's a better dielectric, higher barriers, etc. etc. So I think this is another very interesting presentation that was done this year at LSI 2012. And as I mentioned before, when we were discussing the reset and the fact that you're freezing the state, Robin has some data saying, I don't see that. I still see a lot of things happening in the reset. I don't believe anything is frozen. So he came with the idea there must be some dynamic balance between things. You have a balance, it's not changing very much, but it's dynamic, and things are still moving. And we had some discussions, and I'm going to show what happened at the end. But first, what are the key elements of the model? A constriction. This is actually not so accurate. So this is a constriction, and his model has a top reservoir of vacancies or whatever. Let's call it vacancies. Bottom reservoir and a constriction. The top reservoir, we believe, is mostly the hafnium or region between the hafnium oxide and the hafnium that has, as I show, is enriching vacancies. The bottom reservoir is the rest of the filament below the constriction, and the constriction is basically the part that is being set and reset and changing during the switching. So he made some simple assumptions. So these are the equations. So some things like there's a total number of vacancies involved, and that you cannot change. The shape of the container you cannot change. So the belief was that when you do the breakdown, you're putting a signature of how that filament is going to break and behave for the rest of its life. You can switch it or not switch it, but if you make a very strong breakdown, the filament will be wide, and the way it's switched will reflect that. If you make a better filament which is narrow, it will switch in different ways. So there's some imprint of the way you form the filament that will stay in the rest of its history. And that's, we were saying, the shape of this container or constriction in between. And the number of vacancies he put fixed, saying that, well, the most mobile part of all this is when where switching is happening. It's very unlikely that in other areas you will contribute or oxidize from outside. This is the thing that's the part that you break down is the area where you have most mobility, higher mobility for vacancies. And basically, the dynamic equilibrium was between flows of vacancies between the two reservoirs and the constriction. That was my contribution. And the dynamic balance is on one part, basically the diffusion-like contribution, which is proportional to how many vacancies you have in one side or the other, etc. And the other part was the field-driven part. And taking into account the quantum mechanical nature of the constriction, the field part doesn't act if you're inside the constriction. So all of these things are completely different than many of the models that were around for explaining this type of switching behavior. And I think this is something to look at, to think about. I encourage everybody to also make criticisms, but I think there's something here that's in the right track. So several of the things, this model was very successful in describing the fine details of all the resistograms we've made, and basically we could not find any other model that could do that. Among other things, if you really look very fine, carefully at the IV characteristics, for example in a reset, you start seeing that's not a continuous sort of, you cannot be anywhere, that there are discrete jumps in this thing and discrete levels. So you can be here, you can be here, you can be here, 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 here. So you can start to see, and this was hundreds of these traces all showing the same behavior. So basically, the way to think about is each one of these, you can model, and basically this would be an IV. If you freeze this state, this would be the IV, okay? And this other IV corresponds to a state where you have a different number of vacancies in the constriction, that's all. And the number, again, is as you see, is something that you can count. And it's dynamically changing. Even in the reset, you have these switches between different states. It could also describe the fact that filaments behave differently depending on its initial shape. So a very narrow filament behaves very different than a very wide filament. And so this one I think is the wide one that has this saturation, early saturation effect. To check 64. So this has a much bigger bottom reservoir, 3-4. This has 1E3 as bottom reservoir. What's this bottom reservoir? When you're forming, you're injecting vacancies down, that's the idea, into the bottom reservoir. If you do a very strong form, you make a wide filament, and you have a lot of vacancies in your bottom reservoir, and then basically you saturate quite early, and you cannot basically go into a higher resistance state. And this is a narrower filament. So I encourage you to look at this and hopefully bring criticism. You can also model the set as well. And basically, one of the things that is observing set is that you go in voltage and to some sort of trigger line or transition line or whatever. When the thing suddenly goes, this runaway effect starts, okay? And what determines that trigger, and he in his model said, is the balance between the injection from the bottom reservoir versus the constriction. And the model actually seems to be in quite good agreement with experimental data. So I think, again, there are a lot of interesting things that other models cannot explain. So I encourage you to look at this. Sorry, I'm going the wrong direction. And study, look, and come up with a model that will beat it or whatever. But at least I think there's some interesting features here. Okay, so until what time do I have? Am I past already? Or
10 minutes.
10 minutes more. Good. Okay, so I think this was the main part I wanted to cover. I'll do a few things here, and then. So this comes from Reiner's group, so they recognize it. So basically, in this conducting bridge, you are putting an electrode with very high mobility cations, such as silver or copper, and basically by switching polarity, you're migrating these ions into a dielectric, forming a filament, and then migrating them back, disrupting the filament. This was one of the first type of resistor that was studied very intensely by industry. So Micron and later Kimon that had very big programs in-house. They were trying to actually make products with this. I think the basics are quite well understood. We'll not go into the details of these, but So one of the things we're doing at IMEC is trying to improve the characteristics, electrical characteristics of the switching. Perhaps I should go through this. In the initial systems, we're using a chalcogenide and silver. To start, silver is not manufacturing friendly, so we needed to switch to something else. And one of the issues that was happening is that in this type of systems, there was basically microstructural separation in the nanoscale. We were forming these nanoclusters that were more conductive. If you think about a 5 nanometer cell, you cannot have any granularity in the nanoscale. It needs to be homogeneous materials to start with. So we're moving now into systems where they're more homogeneous and without this type of phase separation. So one of the studies in this direction was looking at copper telluride. I think also mentioned here. Yeah, this was 2007 Sony paper at IDM. Very impressive, very good characteristics. So they use a copper telluride electrode, a very thin sort of dielectric as a medium for the filament. And that inspired basically our work, in which one of the questions we had is, okay, what copper telluride composition may be optimal and why? Because there was no information in the Sony paper, and definitely nobody from Sony would tell us anything. So we did a combinatorial study varying the copper tellurium composition. To do that, we have a sputtering system in which we're putting masks in front of the targets. They're basically a copper and a tellurium target, and the wafer is rotating in front of the target. So each pass, in time it passes, it gets a thin layer from both. But if we're putting masks of these shapes, so that it will be like copper rich on one side and tellurium rich on the other side, and actually we're getting a nice composition gradient across the wafer. So it's a good way of studying this. Complicated slides. Okay, what we found was a strong dependence on the composition, especially on the copper-rich side. For example, for the form, we had a quite different behavior between the very copper-rich side and the rest. And the explanation of this was in the copper-rich side, we're injecting too much copper and making a very strong copper-like metallic filament. The energy required to form the filament with copper telluride was clearly higher. And okay, so in the switching, the most interesting part was in the switching actually. In the low copper content, so a lot of tellurium, low copper, were forming filaments, but they were quite volatile, so they were not stable. And again, we're forming not very strong filaments, etc. On the high copper content, we make filament that we cannot disrupt, which is a massive copper, basically, wire. In the intermediate composition range is where we could form filaments of the right size and characteristics that we can switch very well for a large number of cycles, etc. So there's an APL published on those results. With those results, we'll not get into the details, but okay, this was messed up, but this is the reference. So we could get good cycling, stable with nice characteristics, and then we implemented it into a scale sort of cells, etc. And that work is ongoing. I think, yeah. So this is not too interesting. It's a very scalable technology. So one of the key problems, what's the key problem with CB-RAM? You take a very high mobility ion like copper, right? So that it can move fast with low voltage. Then what happens when you heat it up? It goes anywhere, everywhere. So these things tend to have very low thermal stability. So our fight, not described here in detail, was with thermal stability. How you can make these things to switch fast with electric pulses, but not degrade when you apply temperature. So that's part of the fight. We'll not get much into that. I will skip this. And I also mentioned that we have an activity in mode insulators, vanadium oxide. So at this point for us, it's a curiosity. This transition is around 70 degrees C. That's in the middle of the operating range of a circuit, so not very practical right now. But basically trying to understand, they have some interesting properties. The transition can happen extremely fast. It's we believe electronically driven, although there is a phase transition as well. Okay, so this is the theory that once it's nucleated, it can translate very fast through the material. The nucleation of the transition will normally control the speed. We have made measurements, and I'm going to show, but we don't think we're at any fundamental limit. But it mainly would be a nucleation control issue. So there are a couple of potential applications. We're making films by different techniques, ALD included. Two-terminal devices, we can switch them well. Here the switching is mainly Joule heating. You pass a current, heats up, changes. There are people that disagree with that, but our experiments are fully consistent with Joule heating so far. And we try to make a point. So these are some examples of switching where we can show basically 100 of nanoseconds. But again, we're here far from the limit. If you just calculate after nucleation how the transformation propagates, it's extremely fast. Somewhere in between will be the real switching time of a device. We're not sure, but it will be in a few nanoseconds, I believe. And why this could be interesting, one of the things is endurance is extremely high. We never saw anything fail in endurance, actually, tested. Well, the hafnium oxide showed you 10 to the 10 with a huge effort to get there, right? Balancing this. This material, whenever we switch, we can switch forever. So that was the interesting thing. Okay, I think that's more or less the end of my talk. And I can
Thank you, Jorge, for showing so many results and interesting data. Please.
I'm very curious about the last topic you discussed. So are you saying that this is a material that goes between the metal and the multi-insulator, and while you're applying the voltage, you can actually change the phase of the part in the middle? Is that correct?
Yes, but I think I explained that all our results are consistent with Joule heating. So basically, the material itself has a temperature transition point, right? Yes. As I showed, which is 70 degrees C. You start at room temperature, you pass a current, you have Joule heating, it goes above 70, it switches. So we didn't find anything inconsistent with that. Some people argue it's an electrically driven phase transition. We have not seen evidence that you need to imply anything behind that.
I see. But how would that depend on, you put two electrodes and then the distance between them, that's where you're switching something. Yeah. If you change that distance, and for example, if something is propagating, like this nucleation is propagating, then this time of switching will depend on that in some way. Maybe that would be able to tell you some information now.
Yeah, no, but unfortunately, as I said, the propagation maybe is misleading. I took what we always show, but it's misleading. It shows that it can be very fast. But what controls the switching in our devices is Joule heating, propagation of Joule, of heat, not the intrinsic limit of how fast the phase transition can go.
I see.
So it's just if you do modeling of heat flow, you can more or less see what can happen and how and stuff like that. So it's geometry dependent, it depends on what you put below, on top, heat sinks, all this.
And do you think this is true for all motoristors?
Again, there are several papers in literature claiming exotic effects for the switching. We couldn't we could explain everything with Joule heating. We didn't have to invoke things. So there are some papers, some people that do extremely fast measurements, where they do maybe a femtosecond something irradiation or whatever, and they measure different characteristics. Say, we can see that the electronic transition or this precedes the heating or the blah blah blah. So when you put a lot of energy into a system before it thermalizes, a lot of things can happen. I don't say that that's wrong. But the amount of energy you have is enough after thermalization to get above this temperature. So for our application side, it doesn't make a big difference. If you make a transition without, after thermalization, get above that temperature, that will be very interesting. But I don't think you can. So if you take any of the papers where they can produce a transition, and they say, thermalization happens a little bit after, you calculate all the energy and what temperature it goes above the transition temperature.
Thank you very much.
Other questions?
yeah. Indeed, I said that's why I say this is a curiosity. This is volatile switching, yes. We don't know how to make a memory yet. So potential applications as selector, but it's not very practical either. So at this point, it's just a curiosity, yeah.
Okay. So thank you very much, Jorge.